now we know that there is the concept of an interrupt. We know that there is a generic interrupt controller which actually handles routing the signals to the CPU. Now let's get to the part where we are trying to bind this with our Linux OS and a specific hardware peripheral that we are creating, right. The example that we have been considering all along is our smart timer, right. And as you already know, this would be the entry, this would be sort of the entry that we would have in the device tree, right, corresponding to a smart timer. So we already know what all of this means, right. This compatible term is used in order to decide which driver can bind against this particular device, right. This register information over here tells the OS that this is the particular range of addresses, the physical addresses at which this particular device is connected on the XI bus, right. So this of course has to match with my physical connections on the bus itself. This part of it tells me the size of the address space. The next two lines are new, right. There is something over here called the interrupts line, which as you can see basically has three entries out here, right. So there is this GIC SPI 33 and IRQ type level high, and we will talk about that in a moment. The next line after that talks about the so called interrupt parent, okay. So let us look at both of these lines in a little bit more detail. The interrupts line basically gives me a connection specification, right, which is basically three cells meaning basically these are three numbers if you think about it, right, which are passed on to the GIC in order so that it knows how exactly this particular peripheral is to be connected to the GIC, or rather remember that this is the device tree. This is not telling the hardware what to do, this is basically telling the OS how the hardware has been connected, okay. So you need to always keep that in mind, your hardware has been connected in a certain way and your device tree should reflect that. It's not the other way around. You do not write a device tree and then hope that the hardware behaves in a certain way. You need to know what your hardware is doing and write your device tree so that it reflects what the hardware actually does. The interrupt parent is the slightly easier part. Usually there would be a single GIC in a system on chip, right. So it pretty much just needs to give a pointer to the identifier, the handle pointer in the device tree corresponding to what is the interrupt parent, okay. The three cells that are used for in the interrupts line are basically represent these three numbers out here, right. The first one is essentially the type of interrupt, right, and as we saw over here the typical one would be that the most common one that we are going to be interested in is the shared peripheral interrupt, which means that I would usually have this type over here as the number 0, right, and a 0 over here basically indicates that it is an SPI, a shared peripheral interrupt. If it was a 1 over here, it would indicate it is a private per CPU interrupt, and the numbering also would be slightly different corresponding to that. Now the cell 2 is an interrupt number, right, and for whatever reason, right, even though we know that the SPI interrupts are only starting from number 32, what happens over here is that this IRQ number starts from 0 and we have to add 32 to it, right. So let us say that I have something at IRQ number 7, then I would basically provide IRQ 7 over here, but physically that actually corresponds to interrupt number 39, right, because that is what is connected at this particular location inside the GIC, okay. In the example that we will see later, right, we will take our smart timer peripheral and connect it to the SPI interrupt number 33. So that is the number that we will put in here. What that means is on the GIC hardware it actually corresponds to ID number 65, which is 32 plus 33. And when we see the demo of how it runs inside the kernel, you will see that both of these numbers actually are meaningful as far as the kernel itself is concerned. Now the final number that we have over here, once again it is a hexadecimal number, corresponds to some flags, right, and typically it would simply be, the most common one is just going to be this IRQ type level high, which basically means that it is a level triggered active high interrupt, okay, and that basically corresponds to this number 4. There are other possibilities, you could have an active low interrupt, you could have a rising edge interrupt and so on, right. As I said, the one that we will be considering for MMIO peripherals and our example in particular will be this active high level triggered interrupt. So just the smart timer by itself, of course we have this thing, right, we have the compatibility, we have the register, and we have these interrupts. What that actually means is that we will also have something out here corresponding to the actual GIC itself in the device tree, right. And as you can imagine, look at what this says, right. Basically what it says is that this, since the device tree itself contains entries corresponding to the interrupt controller, that sort of tells us that, look, this is giving us a compatibility string, which means that the OS can actually use this in order to load an appropriate driver, right. So think about it, even the interrupt controller by itself needs a driver. I need to know how to respond to the different kinds of interrupts, how to configure the different interrupts, how to configure the interrupt controller, and so on. It also says that this is the memory map corresponding to the particular interrupt controller, right. So both of these pieces of information are actually useful, right, and are used by the device tree in order to decide what gets connected where.